Moving into section 13.6. We're going to talk about directional derivatives and the gradient. So the topic that we're going to introduce today is really kind of the not really different, but it's one of the after the idea of taking partial derivatives, it's really one of the most important topics that we'll do in chapter 13 in terms of what we'll use moving forward. So we've talked about partial derivatives of functions, and they tell us the rate of change of a multivariable function either in the x direction or in the y direction. So when one of the variables is constant, we're looking at the rate of change moving parallel to one of the axes. Well, what we're interested in today is coming up with a way of finding the rate of change of a multivariable function in any particular direction. So we want to choose a direction and say, how does this function change as we move in this particular direction? So our goal is we have, for what we're going to do now, z equals f of xy, and we want to find the rate of change in z in the direction of some arbitrary unit vector and we're going to call our unit vector in the plane u is just AB, where we're saying we have a unit vector, so the magnitude of u is 1. And we're interested in this rate of change at a particular point. So we're looking at the instantaneous rate of change at some x0, y0. So we're moving in some direction. We want to know per unit direction, per unit of distance that we move in this particular direction, in the direction of this unit vector, how does our function change? So let's draw a picture here of what we're talking about, and then we're going to come up with how we're going to calculate this rate of change. So there are axes. X, Y, what am I doing? I'm thinking rectangular coordinates. Z, Y, X, I was thinking in 2 dimensions. So here's our surface up here. We have our surface up above the plane, some nice surface. And down here in the XY plane, we have our point, some point x0, y0, and that's the point that we're interested in. And we have this unit vector down here in the xy plane. So this is our unit vector. And we have some point down here, q, is just point x at some coordinate x and y. So we're moving from p to q. I'm going to just move this over so it's a little closer to the point. And we're moving from P to Q. So I'm going to draw a vector. I'll draw that one in red. From P to Q. And the unit vector u is pointing in the direction from P to Q. So we're interested in the rate of change of the function z as we move along this vector P to Q in the direction of our unit vector. So I'm going to project these points up onto the surface. So here's one point on the surface, and here's this point. up on the surface. And as we move along, we get a little curve on the surface. And this point is at f of x0, y0. And this point is at f of xy. That's our z value. So the average rate of change of the function as we move from p to q is just the change in the function value, f of xy minus f of x0, y0 over the length of PQ. So we're just taking the change in the function and dividing it by the change in the distance, by the distance that we've traveled in the xy plane. So this is our average rate of change. And we're interested in an instantaneous rate of change. So we're going to take the limit as the magnitude of PQ approaches 0 to get our instantaneous rate of change. So that's going to be our next step. So everybody good with what we're talking about here? Okay? So we're going to take the limit as PQ approaches 0, we could say as xy approaches x0, y0. Somehow we're shrinking down that distance that we're traveling. We're taking that limit. So we're going to write that expression. So we're going to take the limit, the instantaneous rate of change, is the limit, and I'm being kind of a little loose with terminology and the way we normally talk about limits, but we're going to say that we're looking at the limit as PQ, the length of PQ approaches 0, f of xy minus f of x0, y0 over the length of PQ. And we're going to call this limit the instantaneous rate of change of the function as we move in some particular direction. We're going to call this limit the directional derivative. So this is just the rate of change of our function as we move in some arbitrary direction. We're not moving in the direction of the x-axis necessarily or the y-axis necessarily. We're moving in some arbitrary direction. So we call this the directional derivative of f at x0, y0, just adding a little detail here, in the direction of our unit vector. So this is the directional derivative of our function at this particular point in the direction of our unit vector u. And the way we write this, you'll see it written, the symbol for this is capital D sub u of f of x0, y0. So this is our symbol for directional derivative in the direction of u of our function at a particular point. Well, now we have an idea of what this is, what we're talking about. We need a way to calculate this. It's very inconvenient to try to calculate with this limit. So we're going to come up with a way of calculating this directional derivative. So we're going to say, we know that PQ, the vector PQ from one point to the other point where we're traveling is parallel to u. So our vector PQ is parallel to vector u. So what can we do? How can we write, what do we say about parallel vectors? How can we write a relationship between parallel vectors? Their dot product equals 0, and we'll get to something that involves that later, but just if two vectors, what's the relationship between two vectors that are parallel? They're scalar multiples, right? So PQ is parallel to U, so we can write, so we can say that PQ, the vector PQ, equals H U for some scalar H. If we let, and we said that U was the vector AB, so we can say that PQ is HA, HB. And so if we write this in component form, we say that X is just X0 plus H times A, and Y is Y0 plus H times B. What's that? So we're just writing our vector PQ in component form. So as we go from, let me go back to the drawing. If we say that our unit vector is AB and the H is some scalar, so H is going to be the difference in the length of these vectors. So I'm moving H times A in the X direction and H times B in the Y direction to get to point Q. That make sense? Okay. And we're saying that H now, H is the distance that we travel from P to Q. That multiple tells us how much longer our vector PQ is than the unit vector. So H is the distance that we travel. So H is our distance from P to Q. So we can rewrite this limit we're just going to substitute some of these expressions or some of these quantities into this limit. So the limit becomes our directional derivative is the limit as H approaches 0 of f of x0 plus HA, y0 plus HB minus f of x0, y0 over H. So we've just substituted some quantities into this kind of rough expression for our limit, and our limit becomes this. This is how we are going to define the directional derivative. So this is what our directional derivative is, this rate of change in the function as this length approaches 0. This expression defines our directional derivative. So this is our definition of the directional derivative. And this looks like a definition of a derivative that we've seen for single variable functions. It looks like our definition for the partial derivatives. Looks very similar. And in fact, if our unit vector is I hat, we get the partial derivative with respect to x. And if our unit vector is j hat, we get the partial derivative with respect to j. So the partial derivatives are special cases of the directional derivative. So if our unit vector is one of our coordinate vectors, then this definition just becomes a partial derivative. Well, again, we have a definition of our directional derivative. We know what it is. It's the rate of change of our function as we move in some particular direction. We still need an easier way to calculate this. This limits are not generally easy quantities to work with, to calculate with. So we want an easier way to calculate this. Anybody have an idea what we might do with this? All right, let me write something else out, and we want to come up with a process, a way to calculate with this directional derivative without having to use this definition. So we have some function z equals f of xy, and x equals x0 plus ha, and y equals y0 plus hb. And we are trying to find the rate of change of z with respect to the distance h that we travel in the xy plane. So what are we calculating here? Rate of change of z with respect to h, right? That tells us if we're moving, the rate of change of z is our function, and h is the distance we're traveling in the direction of this unit vector. So we're trying to calculate dz dh. What do we need to use to calculate dz dh here? Partial derivatives and the chain rule. We have a function, and x depends on h, and y depends on h. So dz dh, using the chain rule, is, and I'm going to say, rather than dz, I'm going to say df. We can say df or dz. Df dx, dx dh, plus df dy, dy dh. And I could write regular d's here because y0 and a and b are constants, but it's okay. And the other way we could write this is f sub x. And what's dx dh? x0 is constant, a is constant. It's just a, right? Plus f sub y, and what's dy dh? B. Well, df dh is our directional derivative. It's the rate of change of our function as we move some distance h in the xy plane. So this is our directional derivative. And if we say at x equals x0, y equals y0, we're taking the limit as h approaches 0. So we're essentially saying h equals 0. We're taking the limit as h approaches 0. We get that our directional derivative in the direction of u of f of x0, y0 equals the partial with respect to x at our point times a plus the partial with respect to y at our point times b. This is the formula that we're going to use to calculate our directional derivatives. It just involves partial derivatives and the components of our unit vector. And this is going to tell us the rate of change of our function in an arbitrary direction. Now let's look at the form. We're taking, so the directional derivative is when we're taking the limit. So we want that distance that we're traveling, we want that instantaneous. So we're saying that the that h gets smaller and smaller and smaller and smaller.
So if
Yeah.
h equals 0, you plug it into the x equals x 0 plus bk, or you get a.
So again, we're taking the limit as h approaches 0. So we're at h approaches 0, then x is arbitrarily close to x0, and y is arbitrarily close to y0. So we're essentially saying h is 0. But remember that our derivative, when we take our directional derivative, we're taking the limit as h approaches 0. So x and x0 get arbitrarily close together, and y0 get arbitrarily close together. Okay? And I'll just make a little note. We're taking the limit as h approaches 0. So this is the formula that we're going to use to calculate our directional derivative. Just involves partial derivatives and our components of our unit vector. And again, let's look at the form of this. Anybody just looking at this, what does this look like? Just in form. We have a partial with respect to x, so something that involves the x direction times the x component of a vector, plus something partial derivative with respect to y, something that involves y, times the y component of the vector. But it kind of looks like a total differential. Or thinking of vectors, we can a little sip of Tranya here. Something that involves the x components multiplied, added to something that involves the y components. Dot product. This looks like a dot product. So we could say that our directional derivative, and I'm just going to write f, equals, if we have this vector, if we make a vector of the partial with respect to x and the partial with respect to y, dot AB. And I could also write this as, with our curly D's, and we're taking the dot product with AB. So this looks like a dot product. And we're going to do a little bit more with this dot product in just a second. So our directional derivative looks like a dot product, where we have this vector that involves these partial derivatives. And I just want to make a quick, before I say anything else, any questions on what we've done so far? We're doing a lot of exposition to try to get to what the directional derivative is and how we calculate it. So note that if we have, just as a quick note, because this shows up a little bit, if we have our vector, our unit vector defined in terms of an angle theta with the x-axis, and this is our unit vector, and the magnitude of u equals 1. Then our dot product, or our directional derivative, is f sub x cosine theta plus f sub y sine theta. Because this side of my unit vector is cosine theta, and that side is sine theta. So sometimes your unit vector will be defined in terms of this angle. You'll have your vector makes an angle, or the direction that you're traveling makes an angle with the angle theta with the positive x-axis. And then our partial derivative turns into this expression. So just a quick kind of aside. And also note that there are an infinite number of directional derivatives. one for any particular direction that we could decide that we want to travel. So we can define any unit vector u and find a directional derivative in that particular direction. So there's an infinite number of directional derivatives. Now the operation of taking the directional derivative, of using the directional derivative, comes up so frequently. We have come up with, mathematicians came up with a method of computing it quickly, and it has its own symbol. So we get to learn a new symbol today. So we're going to define, because this comes up so frequently, we're going to define the gradient vector. So for some function, and we're saying that our partial derivatives exist, we're going to define call this the gradient vector. And our new symbol is an upside down triangle, del. We're going to define this gradient vector as del f is the partial of f with respect to x in the I direction, I hat direction, plus a partial of f with respect to y in the j hat direction. And if we have a function of 3 variables, then we would just have a df dz in the k hat direction added on there. So this is our gradient vector. Del f is defined as this vector. And we're going to say that del is, we call del is an operator. And we define del, and this triple equals means defined as ddxi plus ddx or ddy j, and if we have a z component, plus d dz k hat. Del has to operate on a function or a vector to have any meaning. These partial derivatives don't have any meaning unless we operate on a function to take the partial derivative, and later on we'll use a del operator and operate on other vectors. So this del operator gives us our gradient vector. The other way that you'll see del notated is, and this is an older symbol, is grad. You'll see the word the word grad, gradient. So del f and grad f mean the same thing. So that book, div grad curl, that's the grad in div grad curl. So using the gradient, we can write the directional derivative very compactly. So we can say the directional derivative of f of xy is del f dot u, where u, our magnitude of our vector, equals 1.
Can you just write the del symbol, or do you have to always have the f?
You could write the del symbol, but writing the del symbol is kind of like writing square root. You have to take the square root of something. Del, the del, it has to operate on something to have any actual meaning. So this is our compact notation for the directional derivative of our function in the direction of u, del f dot u. It's important to remember that when del operates on a function of 2 variables, it produces a vector in the xy plane. It's like a compass direction. So our surface is up above the xy plane, Del F gives us a compass direction in the xy plane. It's just pointing some vector in the xy plane. So our surface is up above, and del F just gives us a vector in the xy plane. It doesn't point in the positive or negative z direction. It only exists in the xy plane when we let it operate on a function of two variables. All right, so that was a lot of exposition to get to this notation, this easy way of finding directional derivatives. So let's look at a couple of quick examples, and then I want to talk about properties of the gradient. And we'll talk about the gradient again tomorrow. So an example, we want to find, we have g of x of y, g of x and y equals the square root of x squared plus y squared. And our unit vector, or our vector, is 3i minus 4j, and we have our point 3, 4. We want the directional derivative of this function in the direction of v at the point 3, 4. So we're looking for the directional derivative in the direction of v of g at 3, 4. Well, the directional derivative of g in the direction of v is going to be del g dot v over the length of v, because v is not a unit vector, so we need to normalize it. So that's going to be our directional derivative. So let's calculate our directional derivative, del g. Let's get our gradient vector. dg dx, what's dg dx going to be? The partial of g with respect to x. X over square root x squared plus y squared. And that's going to be in times I hat. And it's symmetric with y, so the partial with respect to y is just going to be y over square root of x squared plus y squared. J, yeah, the 2 from the x cancels with the 1/2 from the square root. The magnitude of v, to normalize our vector, to get a unit vector, is the square root of 3 squared plus 4 squared. Turns out to be 5. So v over the length of v, our unit vector, we need a unit vector for our directional derivative, is 3/5 I minus 4/5 j. And del g dot v over the length of v comes out to be 3/5 times this. Minus 4/5. I'm going to run out of room here. Oh, we're good. And when we plug in our point at point 3, 4, at 3, 4 we get that this evaluates to negative 7/25. So what this tells us is that at the point 3, 4, g changes by negative 7/25 units for every 1 unit we move in the direction of v. So as we move 1 unit in the direction of v, g is going to change by negative 7/25 units. It's the slope of g in the direction of this vector.
So it's like on the actual surface.
on the actual surface. So it'd be like if you're on a hillside and you say, if I walk in this direction, some arbitrary direction, I'm going to go downhill by 7/25 of a unit for every unit I walk in that direction. That's what the directional derivative is telling us.
It's only at that point.
At that point. So at the next point, if your steepness is changing, then your directional derivative is going to be different at the next point. So at every point, your directional derivative is going to change depending on what your function is doing. So that's what the directional derivative tells us. For every unit that we travel in the direction of our vector, we move negative 7/25 units on this. We change in the z, our z value changes by negative 7/25 units. All right, really quickly, we're almost out of time. I want to tell you some properties of the gradient, and then we'll talk more about the gradient tomorrow. No, it doesn't take up a lot of space. So properties of the gradient. So this del F is a really important quantity, and we're going to use it for lots of different things throughout the semester. So our assumption here is just that f of xy is differentiable. Our first property, if del f of xy is 0, our gradient is 0, then the directional derivative is 0 for any unit vector. So if our gradient is 0, our directional derivative is 0 for any vector. The direction, and this one is a very important one. The direction of the maximum increase. In F is given by the gradient. So the gradient vector points in the direction of the maximum increase in F. And the maximum value of the directional derivative is the magnitude of the gradient. So the gradient tells us the direction of the maximum increase in f of xy, and the maximum directional derivative is the magnitude of the gradient. And the direction of the minimum increase is given by the opposite of del F. Hello? Hi. Thank you. So the direction of the minimum increase is given by the negative gradient, and the minimum value of our directional derivative No, that's just
Okay.
is the opposite of the magnitude of, or the negative of the magnitude of our gradient. The proofs of these are very easy. We'll do those at the beginning of class, I think on Friday. The direction, so the gradient tells us the maximum rate of increase. So if we're on a hillside and we say which direction is steepest, the gradient points like a compass would point in the direction that we would travel to go up the hill in the steepest angle.
How would you know, like when we saw like in the last example, if we don't know the point plug in, we just end up having an equation with like x and y. So how would you?
So at any particular point, the direction of the gradient, whatever so if we plugged in 0.34 into del G,
That's the point we're standing at.
right.
Is 3.4.
So if we're standing at 0.34, if we plug 3.4 in here, the gradient would give us a vector that pointed in the direction of the maximum rate of increase of G.
So you're plugging in the point that you're at.
Right, right. So if we're at a particular point on a surface, if we're on a hillside, we find the gradient, that would give us a compass direction, a vector, and if we walked in the direction of that vector, we would be going up the hill at the steepest angle. If we're going down the hill on at the steepest angle, we would turn around and go the opposite direction. So the negative of the gradient gives us the maximum decrease, or the steepest downhill. And we'll prove those on Friday, but these properties are really important for the gradient. And one thing, I'll talk about that a little later. Okay. Homework. Page 940. All right, one quick reminder, in the plane, if we have a vector in the plane, how do we find a vector that's orthogonal to it, that's normal to it? Switch x and y and change the sign on one of them. Switch the x and y component, change the sign on one, that will give you an orthogonal vector. Talk about it.